Okay, morning everyone. I'll wait for another minute or so we can wait till 8:20. In the meantime, first, uh, the project, it's time to start thinking about projects. So begin worrying about forming project teams, thinking about project ideas, and later this week, we will be posting a list of project ideas, some of which actually have faculty mentors in Pittsburgh and on other campuses. So keep an eye out. So let me start with today's class. This is the last of our series of lectures on training neural networks. We're going to discuss objective functions, regularizations, normalizations, and other issues. This lecture is in two parts. The first part will be done in class. The second part will be a separate recording that I have already made and that we will put up on YouTube and link to the course page immediately after class. Make sure to watch that also because that covers some of the topics that we won't be doing here, particularly dropout is relevant. So uh, please mute yourselves. Here is a quick recap of what we've learned so far. We train networks by minimizing a loss function. And the loss function is the average divergence over training inputs. This loss is an approximation to what we really want to minimize. We've seen that several times. What we really want to minimize is the expected divergence between the true and actual outputs of the network, between the desired and actual outputs of the network over the input space. We minimize the loss using gradient descent, where we initialize W and iteratively adjust it against the gradient. Batch update methods have to process the entire training data before each step of gradient descent, and this is very inefficient because for each update you have to process the entire data. So in practice we use incremental update algorithms. SGD updates the parameters after each input, and mini batch updates increment them using random subsets or mini batches of input. This is faster to converge, but because of the smaller batches, the estimates can have a lot of variance. And so to smooth out, in part, to smooth out the natural variation that occurs due to using these trend algorithms, we like to use these incremental updates. We like to use trend algorithms like momentum, Nesterov, or Adam, which smooth out the gradients using long-term trends and result in faster and better convergence. So this is a quick recap of everything we've seen so far. And so we move on and look at the final topics in the series on training: divergences, normalizations, and other tricks of the trade. Specifically, we are going to consider these following topics: the properties of the divergence and how we choose it. We'll look at batch norm. We'll look at dropout and some of these other topics such as gradient clipping, data augmentation, and other hacks. I've listed these under tricks rather than as something of formal because they are essentially heuristics. Now let's start with the divergence. The loss we minimize is the average divergence over the training data. Now this divergence, as we know, has the property that it is minimum when the network output is exactly equal to the desired output, and it's positive, non-negative at other inputs, at other values. So whenever the network is producing exactly what you want it to, the divergence is 0. If the network is making an error, the divergence will be positive. And so long as we have that property, if our optimization algorithm actually finds the minimum in the loss, which is the average divergence over the training data, then the network will capture the desired output perfectly for the training points. And that is because the divergence as we define it is going to be 0 when y is exactly equal to d. However, The convergence of the gradient descent algorithm depends on other properties of the divergence, how it behaves away from the minimum. And so your divergence function is typically going to have some minimum. We want to get here, but how fast your training converges is going to depend on the behavior of the divergence away from the minimum, because this is where you're going to initialize from, and this is where you're going to sort of travel to the minimum from here. And so, uh, and so the divergence must have a shape to guide the algorithm to the right solution. Also, there are specific characteristics we like to see about how this that gradient, how the gradient of the divergence behaves as we go away from the minimum. Ideally, the divergence must be smooth and must not have many poor local minima. So if the divergence is like this figure to the left, here the x-axis represents the parameter. In all of these figures, the x-axis represents the parameter and the y-axis represents the loss. And so a divergence function like the figure to the left is horrible. Gradient descent simply won't work over here because it's jagged. It doesn't have nice clean derivatives, and it doesn't have a nice smooth structure either. Also, even if it is smooth and has a nice clean minimum, when you're far away from the minimum, you want the gradient descent to progress rapidly, reducing the distance to the minimum in big steps. But when you're close to the minimum, you want the algorithm to be much more careful, taking smaller and smaller steps so that it actually converges to the minimum.
Performing now.
Can you mute yourselves, guys? Right. So this means you want the gradients to be large, far away from the minimum, but small, close to the minimum. A divergence function like this one in the middle, with a small slope far away from the minimum and a very steep slopes close to the minimum, is not a good one. It's the exact opposite of the kind of function you want. This figure in the right, this is the kind of divergence we like. You want the function to be steep away from the minimum, and you want it to be nice and gentle close to the minimum so that gradient descent takes big steps out here and small steps out here, and sort of carefully arrives at the minimum. Ideally, you want quadratic behavior near the minimum. So these figures here should illustrate the reason for the requirements that I just stated. Functions that are shallow, far away from the minimum, are going to have many small derivatives. And this will result in many small steps when you're far away from the minimum. And this is going to slow down convergence of gradient descent when you're far away. On the other hand, if the function is steep near the minimum, then here the derivatives are large, and as a result of this, gradient descent will take large steps and end up overshooting the minimum and diverge. So you have this, although there's a very nice clear minimum and the function is smooth, you have this nasty property that when you're not close to the optimum, the minimum, the algorithm is very slow. And when you're close to the minimum, it sort of takes giant steps and diverges. On the other hand, if your divergence function is of this kind, nice clean bowl, then far away, the function is steep, so it's going to take large steps because the divergence is large. As you get closer, the derivatives get smaller, so the gradient descent steps are also smaller, and it arrives carefully at to the minimum. And in the most ideal case, you're going to get somewhat quadratic behavior out here. So we need a divergence that satisfies, that looks nice. Like we want divergence to look like this and not like this, right? Now, as we've seen before, the most common divergences that we use are the L2 divergence, this one here, and the Kullback-Leibler divergence, the KL divergence. Now, the L2 divergence is the L2 error, or which is the squared Euclidean distance between the output of the network and the desired output of the network. And so, and this is popular when you're trying to predict real valued outputs. The KL divergence is a somewhat more complicated function when we want to perform, that is preferred when we want to perform classification. It's the sum over all classes of the desired output times the log of the desired output minus the sum over all classes of the desired output times the log of the output of the network for the class. We can generally ignore this guy because it's not a function of the network parameters. And this term over here is going to be your cross entropy loss. Now, both of these divergences are well behaved and convex with respect to the output of the network. So if you have a network and you have, say, a single output, the output is y. If I plot y over here, and if I plot the divergence over here, and if this is the desired output d, then the L2 divergence is actually a quadratic. And remember, I said that quadratic divergences are the best, right? So the L2 divergence is going to be quadratic, which is going to give you a nice, clean sort of convergence behavior arriving at the minimum. The KL divergence that we saw earlier was when you have some, for the KL divergence, the behavior is slightly different. The KL divergence looks like this. If your desired output is, say, 1, then the KL divergence comes steeply from infinity and it doesn't even flatten out at the minimum. So in terms of the kind of property that we said we like to see in our divergence, this guy sort of seems to be the better choice than this one, right? So uh, here are the plots of the, but then there's a, but then just because these divergences are both nice and convex doesn't, with respect to the output of the network, y, doesn't tell you exactly how they behave with respect to the parameters of the network. So if you plot this divergence, which is the divergence between the output of the network and the desired output of the network, as a function of the parameters over here, you might find somewhat surprising behavior. Now, again, this L2 divergence is so nice, so nice and bowl shaped. The KL divergence is maybe a little more odd looking, right? But then here are the plots of the L2 and KL divergence as a function of the parameters of the network. In this case, I haven't even taken a full network. I've just taken a single perceptron, which has two inputs, no bias. This is W1, this is W2. The inputs are X1 and X2. The output is a Y, and there's a desired output, D. And I have computed the divergence, and this is my dive, right? So I've plotted dive as a function of W1 and W2. And I've plotted this divergence, I've plotted both L2 divergence and KL divergence. And what you observe over here is, in this case, what I did was to generate randomly drawn positive and negative samples from a problem, from a binary classification problem, and then generated the KL divergence, computed the KL and the L2 divergence for these training data as a function of the two parameters. And here's what you observe, right? Earlier you saw that as a function of the output of the network, both divergences were convex. But as functions of parameters of the network, the behaviors are entirely different. So in our two input case, this is W1, this is W2. These are the parameters of the perceptron. And what do you see? Is this guy convex? Anyone? Is this guy
No,
convex?
it's not.
It's not. This one is convex, right? And which of them has the nicer behavior?
The one on the right.
The one on the
The KL divergence.
the KL divergence. This one looks nicer, right? Both of them still have the minimum at the same point. So you'd find the same optimal parameters with both divergences, but the L2 divergence is now flower shaped. which is basically the ugly kind of shape that we saw that I explained earlier. Whereas the KL divergence is nice and bowl shaped. So even though both divergences are convex with respect to network outputs, so although both of them are convex with respect to this guy, with respect to these two, only the KL is convex, this is not. So simple convexity of the divergence over here doesn't tell you about the behavior with respect to the parameters of the network. And in general, the KL divergence is actually better behaved than the L2 divergence, at least as far as the final layer of a network is concerned. Still, if you go further down, deeper into the network, the behavior is going to become unpredictable for both divergences. Divergences. Also, for regression problems, you really cannot use the KL divergence. But these plots alone should convince you that if you are performing a classification task, you should probably prefer this kind of divergence, the KL, to this one, L2. And so if anybody ever asks you, anytime you see anyone training neural networks for classification, they just blindly use the KL divergence or the cross entropy loss. And I'm fairly confident that most of you didn't question it, but you should, right? What's magical about these losses? Why couldn't you have just used L2? And the answer lies in this figure, that as a function of the network parameters, you can expect better behavior for this guy than for this guy. And so the story so far is gradient descent can be sped up by incremental updates. Convergence can be improved using smooth updates. The choice of divergence affects both the learned network and the results. So Vaidehi, there's a poll over here. Can you post it? Ten seconds, guys. All right, let me stop it. So only the KL divergence is convex with respect to the weights of the final softmax layer. The L2 divergence is not. But both of them have a minimum at the uh, have a distinct minimum at the same location, namely at the answer that you want. So while both of them could lead you to the correct answer, one of them is better behaved. Another problem that arises particularly when we perform mini batch descent, is that of covariance shifts. When we perform mini batch descent, we generally assume that every mini batch has similar distribution as the overall data itself. And so the implicit, basically you're using the mini batch to be representative of the entire data. And so the assumption is that the distribution of the samples in the mini batch is more or less just like the distribution of the samples in the overall data. So if in this figure, each of the colored patches represents a mini batch, and the implicit assumption here is that all of these patches are going to be more or less in the same region of the space. In practice, though, each mini batch may have a somewhat different distribution as illustrated here. In other words, each mini batch has a covariate shift with respect to the others. So this mini batch is generally shifted with respect to this guy. Both of them are shifted with respect to this guy. All of them are shifted with respect to this guy. The mini batches have covariate shifts with respect to one another. And in fact, these shifts across mini batches can be very large. So when mini batch, because mini batch training implicitly assumes that all of the mini batches are similarly distributed, these shifts can affect the convergence of the training very badly. And so we need a solution. The solution to this problem is to shift. Basically, you have each of the mini batches. We know that they are shifted with respect to the overall distribution of the data and with respect to the other mini batches. So what we would like to do is to shift all of these mini batches individually. Every time you get a mini batch, you'd like to shift the entire mini batch to a standard location so that at the end of the day, every single mini batch is now in the standard location as you want it to be. So regardless of whether you're working with this one or this mini batch or this one or this one, because you have shifted the mini batch, eventually all of the mini batches will be in the same location. And now you can expect your training to be uh, better behaved. And so this is, but then how exactly do I know where to shift a mini batch? What is this location and how do I shift it here? For this, we're going to follow a two-step process. First, I'm going to move in each mini batch to the origin to be zero mean. And I'm also going to scale the mini batch samples so that all of the mini batches are now zero mean and unit variance. And then I'm going to shift each of the mini batches to the standard location from here. Now, the advantage of doing it this way is that I don't need to learn a separate shift for every mini batch. Instead, I just need to learn one shift from the origin, and shifting the mini batches to the origin is a trivial operation that does not need that does not need any fancy computation. It does not need learning. It doesn't need a network. And so the and so this process of shifting all of the mini batches to a common location such that the covariate shifts between them is cancelled. And doing this in this manner by first moving all of the mini batches to origin and then moving them all to a canonical shift to the standard location. This operation is called batch normalization or mini batch normalization. We will never generally not use the term mini. We're just going to say batch normalization. So by the way, can you post the quiz? 10 seconds, guys. Let us stop this. And so batch norm accounts for covariate shifts between mini batches, as you see on the slides. Each of the mini batch, you're not speaking of individual instances, you're not speaking of the entire training data. We are accounting for the fact that each of the mini batches has a distribution that's somewhat shifted with respect to the other mini batches. And this is what uh, batch norm actually takes care of. So the most popular answer is right. Now, Uh, so batch norm is generally implemented as a covariate adjustment unit, this little block over here, that happens right after the uh, affine combination of the inputs, the affine computation of the affine value at each of the neurons, but before the application of the activation. So here's where Z is computed. This is the activation. And typically batch norm happens between Z and F. You can actually do it after F as well. And effectively, they're going to be the same thing. But as originally presented, it was presented as being done over here. And so here's Danish.
So folks in the chat have a question. Why can't we keep the mini batch at the origin? Just perform the first step.
Okay. So that's a good question. The point is that if you keep all of the mini batches at the origin, you're going to sort of lose the distinction between the mini batches. You can try this. You're just adding more parameters in an attempt to get some more expressivity in the model. So this step, it's a natural question to ask, why can I not just leave it over here? And you will find that this actually gives you, because you lose a distinction between the different units in the network, all of them are basically going to have exactly the same distribution. So this will generally result in a poorer optimum than having this shift. And this shift, as you will see in a few minutes, is going to be unit dependent. So it's basically adding parameters. And here's something else that happens. The shift actually ends up being a parameter that you compute anyhow. This shift is just the bias in the unit. And so although I'm drawing it in this fancy manner, this is part of the standard computation of the model anyway. I don't know if I answered your question, but again, the fact is, if you have a model that has, a set of weights and a bias, this bias is common to all the mini batches, obviously. So the shift actually ends up being just the bias. So having this shift, unit dependent shift, is like having a unit dependent bias, which we know really helps. Did that answer your question?
I think so.
Yes, no? Yeah. All right. So now something here, right? Batch norm is performed between the computation of the Z and the computation of the F. And the final shift and scaling that we performed over here, this one is actually going to be separately performed for each unit. So you're going to have a different batch norm being done here, then from here, then from here, then from here, which is why I'm claiming that this shift over here is basically the same as adding some value, right? You scale it and then I can add a shift over here, right? That's like adding a bias. And so because it's performed independently for each of the units, that shift is basically the bias term. And we're going to do this thing for each unit. We are going to perform this normalization, shifting the data to the origin and then moving it from the origin to this fixed location for each mini batch. So each mini batch is going to have this operation performed individually at each unit. Now remember that the process of batch normalization is a two-step process. And so we can write this in this manner. We can say first, from the batch, I'm going to shift the mini batch to the origin. Now, if I have a collection of data, you say Z1 to Zn, how do I shift this collection to the origin? Anyone? How do I do it?
Assume it's Gaussian.
Their mean.
Pardon me?
I think you can minus their mean.
Your voice is very muted.
Can you hear me?
Yeah.
Okay, I think you can minus their mean.
You just have to subtract the mean, right? So the moment, oh, what did I do? Come on, move back. This Windows is a pain. I'm not really sure what happened, but okay. So that's exactly what we do. We compute the mean of the mini batch. I'm having some trouble with that. So we compute the mean of the mini batch and subtract it from every Zi. And when you do that, basically you have all of these points over here. So the mean is just the centroid. When you subtract the centroid from the points, that collection is going to end up centered at the origin. Now, in each dimension, I can also divide by the standard deviation. And when I divide by the standard deviation, That's also going to make it unit now. So the two-step process, the first step is to move the entire data to the origin and scale it so that it has unit variance. And then in the second step, I'm going to first scale it back to some spread by this term gamma, which is a neuron specific spread term. And then I'm going to shift it by beta to this new position in space. So in terms of this picture, after moving it over here, first I will normalize the mini batch to have unit variance. Then I'm going to scale it to have some standard spread. And then I'm going to move that to this point. So there's a two-step process. And the first step is that from each U, you just subtract the mean of the entire mini batch, where the mean of the mini batch is just this guy over here, the average. And then you divide by the standard deviation of the mini batch, where we know how to compute the standard deviation. The standard deviation is the square root of the variance. And this epsilon over here is just meant to eliminate division by 0. And then once you do this, if you look at all of the U's over here, the U's for the entire mini batch are all going to be 0 mean, unit variance of 1. And then those U's are going to be multiplied by some gamma to spread them out. And then you add a beta to it. So this is basically spreading it out and shifting it to some new position in origin. To answer the other question, Sam, yes, you could do it after the activation. And I have not seen any convincing argument as to why you should do it in the one place or the other. And you can show that they're strictly equivalent. So here are the two steps. The first step, I can show it in this two-step process. The first step is normalize the mini batch to 0 mean and unit variance, and then shift the position to the right. Of course, in order to do this, I also have to compute the mean of the mini batch and the standard deviation of the mini batch. So if I were to actually show all of the operations more clearly, then this is probably a better figure. This block over here is the block that shifts the entire mini batch to origin and normalizes the variance. And then once you do that, you multiply every value by gamma, and then you add a beta. And then you can see how adding this beta is basically just a bias term, right? So which is why you will have a different bias term, a different shift for every neuron. Now, this is all very fine, but then this really complicates training. A mini batch loss is the average of the divergence between the actual and desired outputs of the network over all the inputs in the mini batch. Now, when you perform conventional training, then the output of the network in response to any input depends only on that input. It does not depend on the remaining inputs in the network. In the batch, it doesn't depend on anything else. And so each of these divergence terms is independent. So when I compute the derivative of this loss with respect to any parameter, I can simply move the derivative into the summation, and I can compute the derivatives of the divergences for the individual training instances independently of what is being done with the remaining training instances. But when we perform batch normalization, something bizarre happens. Namely, because you are normalizing the entire batch, gamma and beta are unit dependent. They're not, gamma and beta are parameters of the network, right? For each unit, you're going to be shifting any batch that comes to the origin to the position defined by gamma and beta. So what happens over here is that when you compute the output of the network for any input, this input is going to be normalized by the mean of the mini batch and the standard deviation of the mini batch. And what this means is that this mean is actually a function of all of the inputs in the mini batch. This variance is also a function of all of the inputs in the mini batch. And that in turn means that the output in response to any input doesn't depend just on that input, it depends on the entire mini batch. And this really complicates the computation of the derivatives. So, does that make sense to you guys? Yes, no? I'm assuming yes, right? So, to understand how this plays out, so here's the equation that actually explains it, right? The mean is a function of all of the inputs in the mini batch. The variance too is a function of all of the inputs in the mini batch. So the output is dependent not just on that specific input, but basically all of the inputs in the mini batch. And this makes it the computation of derivatives challenging. To understand how this works out, let's consider what happens in a single neuron. Within a neuron, so these are the affine values at the, remember, all the inputs come in, you get a plus, you get a z term over here. So within a neuron, you get the z term for every single input in the mini batch. And the batch normalization operation operates simultaneously on all of these guys and produces the normalized, which is the normalized and shifted version of the of each of these inputs at its output. So for each z1, zi, you're going to get a z hat I, where z hat I is the uh, shifted and scaled version where the z has been moved to the origin and then sent to the appropriate location and then scaled. Except the movement to the origin depends on all of these guys. So each z hat now depends not just on this one, but also all of the other inputs. And so when you want to compute the derivative with respect to any one of these guys, you have the loss here. It's not enough to compute the derivative like so. You would actually have to compute the derivative over all of the z hats. You've got to figure out how changing this one z changes every one of these z hats. And the variations in those z hats are going to affect the loss. And so that's what we're going to have to contend with. Let's see how the math works out. Let's expand out the operations and compare them to the figure we originally had for batch norm, which we have at the top over here. So the batch norm is this two-stage process, centering the data and then shifting it to the right location. So the centering in the data block is the one where the operation considers the entire collection of inputs. So this data centering operation, and in fact batch norm in general, if you look here, this is actually a vector operation. It's not a scalar operation, but it's not a vector over a vector in the conventional sense. The components, the vector components going in are the z values for the entire mini batch, and the vector components coming out are the z hat values for the entire mini batch. And so when you look at the batch normalization operation, this centering operation is the primary vector operation, which is where you actually, if you look at the figure closely, you're going to see that there is a mean and a variance being used here. This mean is a function of all of the z's. The variance is a function also of all of the z's as well as the mean. And then the centered value u is a function of the corresponding z, but also the mean and the variance. So the centered value u is a direct function of the corresponding z and an indirect function through these guys of all of the other z's, right? But once you compute the centered value, thereafter, z hat is simply going to be gamma u plus beta, right? So the shifting and scaling operation is performed independently on each of these u's. And so this is so when you zoom in on batch norm, there's a combination vector operation and a scalar operation. So what this means is that we can compute the derivative of the mini batch with respect to each of the ui's individually during the backward pass. But when we compute the derivatives for the zi's, we have to consider the entire mini batch. So let's see first how we would compute the derivative with respect to the u's. Here, as the forward pass at a single neuron for a single training instance from a mini batch. The neuron computes its affine value Z. Then we need not consider the bias. So you can think of it as a linear combination, because as we saw, this shift over here grabs the bias, right? So the neuron computes a linear combination, which I'm going to represent by Z of its input. And then the first stage of the batch norm computes U from Z, except U is actually going to use as additional parameters the batch mean and batch variance. And then it shifts the U to the new position Z hat by scaling it by gamma and then adding a beta to it. And that gives you the final Z hat. So during back propagation, we are first going to compute the derivative. As you propagate backwards, you would first get the derivative of the divergence with the loss with respect to y. Then you can move that past here and just multiply this derivative by the derivative of the activation function, and you're going to get d loss over dz. And now this second block over here. So we've already, as you're going backwards, you've already got this term. This block over here is the one that computes z hat from u, right? So if I have d loss over dz hat, then it follows from this equation that d loss over d gamma is going to be d loss over dz hat times u. And so I can compute the derivative with respect to gamma. Similarly, I can write d loss over d beta is simply going to be d loss over dz hat. And so I can compute the derivative with respect to beta as well. And these terms, beta and gamma, are learned parameters. And so these terms are going to be used in batch norm to learn, in gradient descent, to learn the parameters. And then I can take a step back and use the same equation over here. And when I use this equation, I get d loss over du is simply going to be d loss over dz hat times gamma. And so working my way back, I can actually compute the derivative of the loss with respect to this u term for the input. And so now is where it gets interesting. Over the mini batch, how did I get this strange red line? It's on every slide. Maybe I can erase it.
Someone else has annotated on the slides.
Whoever it is, delete it, guys. Right. So there's got to be a way of fixing that. How do I? We live with it, but this is not nice, all right? Be careful, for guys, and whoever did that, please erase it, because it's going to take time away from the class. Okay. So in the process, what we have done is that we've gone backwards and computed the derivative with respect to these u's for every instance in the mini batch. So now we have this the dl over du for every single training instance in the mini batch. Now, from these u's, we want to compute the derivative with respect to the z's. And let's see how that happens. Here is the complete set of dependencies between the z's and the u's. These are the z values for the entire mini batch. Each one comes from one training instance in the mini batch. All of the z values are used to compute the mean of the mini batch. All of the z values are also used to compute the variance of the mini batch. The normalized u is going to use the z, the mean, and the variance, the standard deviation, but that's derived from the variance, right? So you can see that if I look at basically every z influences every u. And so if I want to compute the derivative with respect to of the loss with respect to any z, I actually have to I have to sum over all of these u's, and I'm going to sum the d loss over du times du over dzi. And the the tricky piece that I have to compute over here is this. We already have d loss over du going backwards, and so we got to figure out how to compute this for every ij pair, for every ui and for every zj. How do I compute d for every uj and every zi? How do I compute duj over dzi? So now here, yes, there's a poll. All right, 5 seconds, guys. All right, stopping it. So every UI depends on every Z, right? Every U depends on every Z, but every U does not depend on, there should have been UIs. I'm not sure why the U is missing. Every U does not depend on every other U. So the first term was right. There's something broken here. And batch norm is really just a vector operation over all of the ini inputs in the mini batch. So
The
which is
second
basically,
option
yeah.
in the first question is post-normalized, but the first option is pre-normalized.
So the first option says that every U is a function of every Z. The
Yeah,
second
and the
option,
second option says it's post-normalized.
so I'm not able to hear you clearly. Could you repeat that? Or type it maybe?
I'm not sure why it's not the same today, but can you hear me now?
Yeah. So the normalized is so this is U is normalized, right? Meaning it has been centered and the variance has been made 1.
Yeah,
And
but
Z
what
is
I
not
mean,
normalized.
yeah, what I mean is the first question's 2 options are different.
Correct. Right. The second option is kind of post. So I'm calling U post normalized and Z pre normalized. The second option didn't appear properly on Zoom. And so this is a Zoom issue. That was supposed to be a UI. So the problem here is the first option said every U is a function of every Z. The second option said every U is a function of every other U as well, which it is not.
Oh, I see. Thank you.
Right? Okay. So now let's look at how we can compute. So let's consider the direct case. What happened to my eraser over there? My eraser is gone. Okay, let's consider the direct case. So this is DUI over DZR. Like, as an example, I'm going to use U1 and Z1. So they are both in the same line, right? So if you look at this direct case, what are all the ways in which U connects to Z? Let's take a look. First, there is the direct line, right? So the derivative of U with respect to Z has a partial derivative over this direct line, plus now there is this line, right? So there's the where first you computed mu from Z and then you compute U from mu. So it's going to be the partial of U with respect to mu times the derivative of mu with respect to Z. So this is the second line, right? And then there's the third line, which is like so. Z affects sigma squared, and sigma squared affects U. So you're going to have the derivative of u with respect to partial of u with respect to sigma squared times the full derivative of sigma squared with respect to z. So does everybody see how this equation came about? Is this clear, guys?
Yes.
So it's pretty much right. It's very straightforward. And now the rest of it is just kind of tedious math. Okay. So let's sort of work it out. Here is the complete derivative for the through line. dui over dzi is the partial over the direct line, the derivative over the mean branch, and the derivative over the variance branch. Let's compute these terms. Let's compute this first term over here. This is the partial derivative of u with respect to z computed over the direct path. That's going to come from this equation over here, right? That is the one that gives you the direct relation of u to z. And so if you just work it out, it says ui equals zi over sigma square root of sigma squared minus mu I over square root of sigma squared. I just separated it out. So which immediately gives you that the derivative of u with respect to z is simply 1 over square root of sigma squared plus epsilon, because that's what we use. So let's just replace this term over here by the term we got for it. Now let's consider the second term, the derivative of u with respect to mu. Can anybody tell me what that is going to be? Anyone? That's also going to come from this equation, right? Yeah.
Minus 1 by under root of the square.
Minus 1 over the square, minus 1 over square root of sigma squared, right? So that's simply going to be minus 1 over square root of sigma squared. So let me plug that in. Okay. Okay. And now let's consider this term. This is the derivative of mu with respect to zi. Which equation is going to give that to you?
First equation.
The first equation, right? And from that, you can directly see that d mu over dzi is just 1 over b, right? And so that's because mu equals 1 over b times z1 plus z2 dot 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 plus zi plus the remaining z's. And only this is the only one that you're taking the derivative with respect to. And so that's going to give you just 1 over b. So this one's easy. I can replace that. And now, this is the expansion we have so far. We have a couple of more terms to compute. So let's consider those. Let's consider this value next. That is the derivative first. This guy. Which equation am I going to get this derivative from? du over d sigma squared. This term here, right? And what will it be? I can write this. It's fairly trivial.
1 upon 2 under root sigma b square plus e.
Yes, so because I can say u equals z minus mu over square root of sigma squared plus epsilon, which I can say u equals z minus mu times sigma squared plus epsilon raised to minus 1 over 2. So du over d sigma squared, I'm taking the derivative with respect to sigma squared, okay, is going to be whatever z minus mu times minus 1 over 2 times sigma squared plus epsilon raised to minus 3 over 2. Correct? Everyone?
Yes.
This is just straightforward high school arithmetic. And so I can write that. And let me plug that value over here. And so now we have only one final term to compute, which is this one here, dz sigma squared over dzi. Now, which are the, if you look at this dependence figure, which are the connections that are going to get activated? Why ask you the question? I'll give you the answer, right? So this is what you're going to have. Sigma squared is connected to Zi through two terms. Look at this equation over here. It's directly connected to Ci because every Zi directly influences sigma squared through this one. But every Zi also affects mu b, and mu b in term affects sigma squared. So the derivative, the full derivative of sigma squared with respect to Zi is going to be the partial derivative of sigma squared with respect to Zi over this connection plus the derivative over this connection, which is the derivative partial of sigma squared with respect to mu b times the derivative of mu b with respect to Zi. So is everybody seeing where this equation came from? Guys? Yes, no?
Yes.
Right? Right? Very easy. Okay, what is this term? Sigma squared over Ci.
1 by B 2 Zi.
So that's going to come directly from this term, correct? And so that's simply going to be 2 times. I take the derivative, it's 2 over B sigma minus mu, correct? The straightforward derivative of the computation of the derivative. So this one's easy. What is the derivative of sigma squared with respect to mu? That's also going to come from this equation.
Minus 2 by B.
And yes, okay, let's work it out, right? That's going to be sigma squared equals 1 over B summation I Zi minus mu B squared, right? So d sigma squared over d mu is going to be 1 over B, 2 over B summation I Zi minus mu B. What is this term? Remember, mu B is 1 over B summation I Zi. So what is this term?
That's 0.
It's going to be 0, right? Because you're basically saying when I center, what is the average of the center? This is the center shifted version of Zi. And I'm asking you the average of the center shifted version of Zi. So the derivative of sigma squared with respect to mu is going to be 0. And so you're going to get this term here, which tells you that the derivative of sigma squared with respect to mu is 0. And consequently, this term is 0, which means I don't even need to know what this guy is. And so that is the derivative of sigma squared with respect to Zi. Let me plug that in here. And I have this kind of ugly looking equation for the derivative of u with respect to ui with respect to Zi. I can simplify it a bit. And this is what it's going to be. So this is the derivative of ui with respect to Zi. Obviously, you don't need to memorize this equation, but it's going to be very trivial for you to derive it again on your own if you should so desire, right? So I have a full formula for this through connection. What about a derivative of this kind, which is not a through connection? What will that look like? Anyone? So the derivative of the cross line is just going to be this term plus this term, which is identical to the equation for the I equals j term, except without the direct line, right? So this, the derivative for the cross term is going to be the same as the derivative for the through term, except this guy is going to be missing. So this partial came over the direct line, which you don't have from the cross terms. But the other two, for these two, the computation is exactly the same, right? And so you're going to get the derivative of uj with respect to Zi ends up looking like so, which you can write out. We know the terms. There's no need to actually derive it. We know what they are. There's no need to even explain it for now, but bear with me, we will. And so when I speak of the derivative of any ui, uj with respect to zi, I get this equation with 3 terms for the direct path and 2 terms for the cross paths, where the derivative for the cross path is the same as the derivative for the through path, but without this first term, right? And so remember, we went through all of that computation, all that painful derivation, because we wanted to compute the derivative of the loss with respect to any zi. And that derivative we saw is given by this formula over here. You've got to sum over all the u's, the derivative of loss with respect to u times the derivative of u with respect to z, right? And so putting it all together, here is this kind of ugly looking function you get. At the top, I've simply reiterated the function for the derivative of u with respect to z. Now the derivative of the loss with respect to any zj sums over all of the u's, and the derivative of any uj with respect to zi, it has this extra term for the through path, for the remaining paths, and all paths have this common, these 2 terms in common. Now, I have sort of glossed over these terms so far, but then let's actually look at it a little more carefully. The derivative of the loss with respect to zi gets this term from the through connection, okay? It gets this term over here from the, here the summation is over the entire mini batch. So this is going to be the sum, you know, both this guy for the through path and this one for all the remaining paths. And then you get this other summation term, which is also summing over the entire mini batch. Now, observe something over here. The derivative of the loss with respect to any zi is the same as the derivative with respect to the corresponding centered ui to within a scaling term. But you also subtract out from this derivative the average derivative for the mini batch, right? This guy is the derivative for just that ui. This is the average derivative for the mini batch. So are you seeing the relation between these two terms, guys? Can you see this? So this is simply, ignore the scaling term. I can write this as dl over dui, right? And this is 1 over v summation j dl over duj. So now, if the mini batch consists of all identical samples, what will this term become? Anyone? What will this term become?
0.
It's going to become 0, right? Because dl over du is going to be the same for every term in the mini batch, correct? So the average is going to be the same as this term because they're all the same. All the elements and entries in the mini batch, all the samples in the mini batch are identical. All the u's are identical. And so this term is going to become 0, right? Now, what about this term over here? If all the samples are identical, what is the second term going to become? Also 0, right? Because I can just write dl over du, that comes out, times summation z minus mu squared. But then if all the samples are the same, this z equals mu, so this is going to become 0, this becomes 0 as well. So what does this tell us about the derivative of the loss with respect to zi if for some unfortunate reason all of the samples in the mini batch are identical? What will happen to your derivative? Anyone?
It won't change at all.
It won't change at all? It's going to go to 0, right?
Yeah.
right? So if your mini batch is a collection of all identical samples, then right at that batch normalization operation, the derivatives, no, it doesn't mean the batch is already centered. It means the batch is all identical samples. So what will happen is that as you perform back propagation, when the derivatives hit that batch normalization layer, when they go past the batch normalization layer, all the derivatives are going to become zero. And subsequently, all further derivatives downstream are also going to be zero. So batch norm, if your batch consists of all identical samples, it will kill back propagation. Is that making sense?
Yeah.
So basically what will happen is if I have batch norm, then I'm going to compute Z, and then I have this Bn, and this is going to give me Z hat, and then other stuff happens. This happens for the entire mini batch. Now, when I go back propagate and I do a D loss over dz, that's going to become zero everywhere. And as a result, further back propagation is going to give you no derivatives at all. Back propagation is going to give you useless results. And this is going to happen even if the instances in the mini batch are not necessarily identical, but very similar. So then too, the net derivative that gets back propagated through batch norm is going to be quite small for the mini batch. So batch norm actually works best when there is some diversity amongst the instances in the mini batch. If your mini batch is too consistent, then simply the act of introducing a batch norm layer can kill your training if your mini batch isn't consistent. Is it making sense? Yes, no, guys? Okay. So there is a quiz over here, poll. Can you release that by the way? Okay, 5 seconds, guys. Let me stop this. So this is true. Batch normalization effectively blocks back propagation and prevents gradient computation if all instances in the mini batch are identical or very similar. That's basically what we just saw. Now, batch norm eliminates covariate shifts by, uh, so now we've computed the derivative of the loss with respect to the affine inputs at each of the neurons. We have the d loss over dz, and we can continue back propagation from here, propagating this derivative further backwards. Now, batch norm eliminates covariate shifts by normalizing out mini batch means and variances during training, right? But what about inference at test time? Now, typically at test time, you're not providing mini batches with their own covariate shifts. We cannot compute a mini batch mean and a mini batch variance to perform the first stage of batch normalization. So instead, what we will do is we will compute for the means and the variances that we are going to use in BN. We will use the average of the mini batch means computed over all of the mini batches in the training data. So this is going to be the average of the mini batch means computed over all training mini batches. And similarly, we're going to use the average of the mini batch variances over all of the mini batches. And we will use these within this first block during inference. Now this is a bit of a heuristic, but this works. And all of these averages, they're going to be computed from the final converged net. Now, one small difference, when you compute the average of all of the variances, we actually use the unbiased average, which is going to, the unbiased estimate of the variances. I won't get into what that means, but there's this B over B minus 1 factor over here, where B is the mini batch size, and that gives you a more stable estimator for the variance. So now batch norm is a neuron-wise operation. We don't need to apply to every neuron in the network. You could apply to just some of the layers or even to only some of the neurons. It generally improves both convergence rate and the network performance. And empirically, we also find that BN often eliminates the need for dropout, which is another common regularization technique that's there in part 2 of this lecture. And so, but then to get the maximum benefit from batch norm, during training, the learning rates must be increased and the learning rate decay can be faster. And that's because the data are normalized, they end up being normalized, so you get better gradients, and having a larger learning rate gets you faster convergence, but to counter it, the decay must be faster. And again, BN works best if the data within each mini batch are sufficiently diverse. Otherwise, it can actually end up blocking the derivatives from back-propagating. So this means it's going to be critically dependent to have better randomization of the training data. You need good shuffling for batch normalization to be effective during training. So if all goes well, then BN can result in very big improvements. Here are some plots from the original BN paper. These results are on ImageNet. The x-axis is the iteration number. The y-axis is classification performance. The authors test various variants of BN that they propose, and you can see that in every case, the use of BN greatly speeds up training with respect to the baseline. So this is the baseline, and you get that performance much quicker when you perform BN. Also, the actual classification performance finally is much better when you use BN than when you do that. And so here's the story so far. Gradient descent can be sped up by incremental updates. Convergence can be improved using smooth updates. The choice of divergence affects both the learned network and the results. And covariate shift between training and test may cause problems and may be handled by batch normalization. So any questions?
I have a question.
Yeah.
How do you determine gamma and beta?
So gamma and beta are learned parameters. So observe that over here, we remember beta is really just the bias for the neuron, right? So when we performed our computation over here, by the time we got to this, to U, we had already computed the derivatives with respect to beta and gamma. So you use these within, within your standard gradient descent, and you learn beta and gamma for every neuron. Beta is really just the bias, and gamma is a scaling parameter. Did that answer your question?
Yes, thank you.
Okay. So I'm going to sort of spend a few minutes when talking about data under specification, but as this is explained much more in detail in the auxiliary lecture that I have recorded. And because I recorded it, I actually was slower in this lecture than I needed to be in this first part. So the key thing here is, yeah.
So this question was asked in chat way earlier as well. But so the original paper proposes placing batch norm between the linear layer and the activation function. But I've seen online, and I'm sure others have also seen this, that some
I did
people have
mention,
proposed.
I did mention this, right? It doesn't matter. This is just, I'm only explaining it as having been done here, but you could do it as over here as well. think about what is happening when you do this, right? If I have a bunch of neurons, if I'm actually performing batch norm at these locations, that effectively propagates to the affine values at the next layer. So performing batch norm over here is 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 kind of equivalent to performing batch norm over here. This is just a linear transform, right? And so performing batch norm before or after a linear transform is not going to be vastly different.
Right, but I think some of the posts online and even some code that was written by the original author of the paper seems to prefer putting it after the activation, i.e. before the linear layer.
It's so, but seriously, if you want to really think about it, there is a weight function. You could, what we are doing is performing batch norm after Z over here, right? Or you could perform batch norm over here. The two are just related by this weights matrix W. If this weights matrix were a unitary matrix, then the two are going to be strictly equivalent, right? If but for others, it's going to depend on the nature of the weights matrix. But for typical networks, it shouldn't make a difference,
All right, got it. Thank you.
right? It's just a linear transform.
If the beta is actually the bias, does it mean that it doesn't need to be learned?
The beta is learned, right? The beta is learned, but that means that you don't need to have an explicit bias for each neuron anymore.
Oh.
You don't use a bias. Okay, let's skip that. But if you're performing batch norm, then in the neurons where you're performing batch norm, you actually don't need an explicit bias term because the beta captures the bias.
Yeah, but like
having an extra bias is only
in the original neural network without the batch norm, isn't the bias term like always the same? So we don't need to learn that, right?
no, you learn the bias, right?
Oh, right.
You always learn the bias.
Okay. Yeah, sorry.
Correct. So the way to think about it, the correct way to think about it is, I should say that I have these weighted sums. There's a plus, and then there's a second plus, and there's a bias that comes in, and this is where the activation applies, correct? And the reality of it is batch norm is not performed here, batch norm is performed here. Does that make sense?
Yeah.
So in that sense, this is just a standard parameter that you're learning. That's it.
Okay.
The only other thing that you're learning is a weight out here. So you can think of this as, you can think of batch norm as some layer with no parameters to learn. But then after batch norm, the output is passed through a single weight and a single bias, right?
Yep.
So I'm kind of out of time. Just give me a couple of minutes. I'll sort of rush through what this and the rest of it is in the auxiliary lecture. Now, in all of the figures that I've given you so far, there was a little bit of an exaggeration. I said that we're going to attempt to learn an entire function from just a few snapshots of the function, right? And the way we did it was that we defined a divergence between the function value at each point and the actual output of the network at each point. And we minimize the average divergence across these training points to learn the network. But that only guarantees that you are able to learn the value of the function at these points, right? It doesn't say anything about what happens outside of the points. And so, while you might be wanting to learn this dotted curve, there's nothing in the whole process that stops you from learning this perfectly useless red curve. And this is something that is really an issue that you have to worry about. Now, how bad is this issue? To give you an example of how poorly you provide your network with data, consider like you are working on 100-dimensional binary data, right? 100-dimensional data are tiny data. It's like a 10 cross 10 image. And 100-dimensional binary data is like a 10 cross 10 image of binary pixels. Even in 100-dimensional binary data, there are 2 raised to 100 possible inputs, which is about 10 raised to 30 possible inputs. And because the data are binary, the data are all going to live on the corners of a binary hypercube. Now, to learn the function fully, I need to know the function value at every one of these corners. If I provided 10 raised to 15 training instances, 10 raised to 15 training instances is like 1,000 trillion training instances. And if I gave you 1,000 trillion training instances to learn this function, and this is a really tiny function, right? Just a 100-dimensional binary input. You would think it's enough? Nope. You are going to be off by a factor of 10 raised to 15. Basically, it's as if you had no data at all, right? To give you an idea that even in this tiny example, and if I give you 1,000 trillion training instances for this tiny example, to give you an idea of how bad it is, suppose just imagine all of my data live on a hypercube where every edge has some finite length L. It can be tiny, it can be very small. And then I put you in a little spacecraft and sit you over here, and you travel at half the speed of light. I just drop you at a random corner. And then you begin traveling along the edges of the cube, trying to search for one of your training instances, one of the 1,000 trillion training instances that you just gave, right? What would happen is that the life on Earth would end and the sun would explode before you found that first training point. That's how sparse your training data is. Or to give you a different perspective, if I sort of logarithmically scale down the training data by a factor of 100, what you find is that you get on average something like 1.000000001 data instances per dimension. And you're asking the poor network, yeah, here's this data, learn the function, right? It's absurd. You're not going to be able to learn the data function from just one data point per dimension. And this is really the task that we try to perform. And so clearly, that's not going to be feasible, right? And so we need smoothing constraints, additional constraints that tries to push the model into filling in these missing regions acceptably. And I will stop over here, but the gist of it uh, is that in order to do this, you will need to you'll have to need to do 2 things. A, enforce the requirement that all of the weights of the network be as small as possible. And secondly, given a fixed certain parameter budget, you must always prefer deeper networks over shallower networks. So that bit is explained in the first 5 or 10 minutes of the auxiliary lecture. Please look it up. The remaining half hour of the auxiliary lecture is about dropout, explaining dropout, and some of the other heuristics. Please do watch the lecture. So I'll stop here and take any questions. Any questions? So for LSTMs, having n-dimensional sparse vectors to represent words in a one-hot format is generally a bad idea. Okay, so let me shock you, right? We will encounter this topic when we are talking about recurrent networks and LSTMs. It's going to be in several weeks. But then if you're providing how much, if I'm giving you a 10,000 dimensional space and I put 10,000 points in that space, how much of the space are you using? Basically nothing, right? 0. So One-hot representations are a tremendously inefficient use of the space. So, yeah, yeah, exactly. We'll get to that when in that lecture. Is gamma a scalar or a weight matrix? You're going to get one gamma term for every neuron, right? You can sort of try to cast it as tensor operations, but effectively you're going to get one gamma term and one bias term, one beta term for every neuron. All the way until gamma and beta, you can think of those as matrix operations. But when you actually try to go from the derivative with respect to u to the derivative with respect to z, then you have to go across the batch dimension. I'll stop the recording over here.